This is section 2.7a, nonlinear inequalities. A quadratic inequality in one variable is an inequality which can be written in the form ax squared plus bx plus c is greater than 0, with a not equal to 0. Of course, the symbols greater than or equal to, less than, and less than or equal to may also be used. And of course, you also know that from Algebra 2. And also this course, when the times that we have done inequalities. Here's an example of a quadratic inequality. X squared minus 3x plus 7 is less than or equal to 0. 3x squared is less than x plus 5 is a quadratic inequality, since it can be written 3x squared minus x minus 5 is less than 0. And in this section you'll encounter some inequalities that are not written with a 0 on one side, but you can modify them and manipulate the terms in such a way that you will get a 0 on one side. X squared plus 3x is greater than or equal to x squared plus 4 is not a quadratic inequality, since it is equivalent to 3x minus 4 is greater than or equal to 0. And that's just because the x squareds cancel out. Alright, so this is not really anything new, because I'm sure that you've done these kind of inequalities before in Algebra 2, but it is important to review these concepts because they're easy to forget, especially when it comes to solving these inequalities. The solution set of an inequality is the set of all numbers that satisfy the inequality. Study the graph, for example, of the solution set of x squared plus 3x minus 4 is less than or equal to 0. This is what that solution set looks like on the number line. And we're going to be using number lines a lot for inequalities. They're very helpful to visualize solution sets. A couple things to point out about this particular solution set. First of all, don't worry about how you get it, because we're going to be spending the rest of today on that, on how to find the solution set. But first of all, let's understand what the solution set means. It means that where this red line is, that red line represents all the points, all the x values that will satisfy this inequality. Notice also that there is a bracket at the end, the right end of this interval, and there's a bracket on the left end of the interval. And as you remember, brackets indicate that the endpoints are included in the solution set. Now the solution set can be written in interval notation as follows: bracket -4, comma 1 bracket. So how do we get that? Well, these are the steps to find the solution set for a quadratic inequality. It's not the only method, but I'll go through one method first on this screen and the next, and then we'll get into another method after. The following method can be used to solve quadratic inequalities. X squared plus 3x minus 4 is less than or equal to 0. You first, of course, write the quadratic inequality. That's the kind of step you might look at and say, duh, seems stupid, obvious. But believe it or not, sometimes just writing the problem correctly is half the battle, and sometimes writing it incorrectly is the source of error and frustration. So just simply rewriting the problem is never a waste of time. X plus 4 times x minus 1 is less than or equal to 0. This is simply the factored form of this quadratic inequality. And then once you factor, well, then you can set up a disjunction. And we've done that before with a few problems that have come up, but this should refresh your memory. We set it up like this to solve. X plus 4 is less than or equal to 0, and x minus 1 is greater than or equal to 0. Or, and that's what I was referring to when I said disjunction, because or is a disjunction. Grammatically, it's a disjunction, okay? But mathematically, or indicates a union. Now, you don't need to understand what I said just now, because I think when I show you the solution set, that'll become clear. X, and then continuing this disjunction, we have or x plus 4 is greater than or equal to 0 and x minus 1 is less than or equal to 0. First of all, let's figure out and let's understand why this is true. Look at the factored form. I have x plus 4 times x minus 1. X plus 4 is in parentheses, x minus 1 is in parentheses. But the key here is to look at the inequality sign is less than or equal to 0. That means that there are only two possible ways for me to get a negative number when I'm multiplying two numbers together. And that's the following. Either the first number is negative, that is, either x plus 4 is negative and x minus 1 is positive, because positive times negative is negative, or x plus 4 is positive and x minus 1 is negative. Okay, so either the first one's positive and the second one's negative, or the first one's negative and the second one's positive. And that's the only way that I can get negative numbers. All right, that's why I set up this disjunction. Now remember, when we're talking about math, and means intersection. That is what's common to both. Or means union, and that's joining things, whether there's common elements or not. Okay, so it's important to keep that in mind. These are concepts you've learned, but they're easy to forget. And the other thing that's tricky about it is we tend to think of union as, putting things together, and so naturally, if we look at this just from a grammatical point of view, we might be tempted to say, oh, and must indicate union, and or must indicate intersection. Well, that's totally false, okay, because and means it has to be true for both. That's intersection. Or means it doesn't have to be true for both. That's union. All right, so we set up this disjunction. Here's what it looks like when we go through the solution. We simply solve each of these simple inequalities separately, but we keep the ands and ors. And we have x is less than or equal to negative 4 and x is greater than or equal to 1, or x is greater than or equal to negative 4 and x is less than or equal to 1. Now, continuing, we have empty set here. Why? Because if I have x is less than or equal to negative 4 and x is greater than or equal to 1, there is nothing in common, right? X less than or equal to negative 4 is one set of all real numbers less than or equal to negative 4. X is greater than or equal to 1 is another set, the set of all real numbers greater than or equal to 1. Well, those two sets have nothing in common, therefore their intersection, indicated by and, their intersection is empty set. Or, and now this is our union, or, and we have this solution over here, negative 4 is less than or equal to x is less than or equal to 1, because that's the common area of these two sets. One set's x greater than or equal to negative 4, that's all real numbers greater than or equal to negative 4. And the next set is x is less than or equal to negative 1, x is less than or equal to 1, which is all real numbers less than or equal to 1. When we take or find the intersection of those two, we end up with this common area. Negative 4 is less than or equal to x is less than or equal to 1. Now, we can always do a union with any other set, but since we're doing a union of this set with empty set, the empty set disappears, and we're left only with negative 4 is less than or equal to x is less than or equal to 1. And that is the solution set of bracket negative 4, comma 1 bracket. Example, solve and graph the solution set of x squared minus x is greater than or equal to 6. Now you should be able to do this on your own based on what we learned in the last screen. Pause the video, do it on your own, and when you've found a solution set, then resume. Alright, going now through the solution, we rewrite the inequality. First step, x squared minus x minus 6 greater than or equal to 0. That's because we want 0 on one side. X plus 2 times x minus 3 is greater than or equal to 0. We factor. Then we set up our disjunction. And the reason we set it up this way is because now I'm looking for positive numbers. Numbers greater than or equal to 0. It could be 0, but I'm basically looking for positive numbers. And the only way that I can get positive numbers when I'm multiplying two numbers is either for both numbers to be positive or both numbers to be negative. And that's why I set it up like this. X plus 2 is greater than or equal to 0 and x minus 3 is greater than or equal to 0. Or x plus 2 is less than or equal to 0 and x minus 3 is less than or equal to 0. Continuing with the solution, we have x is greater than or equal to negative 2 and x is greater than or equal to 3, or x is less than or equal to negative 2 and x is less than or equal to 3. We are now looking for the intersection of these sets, right, of x is greater than or equal to negative 2 and x is greater than or equal to 3. What's their intersection? It is x greater than or equal to 3. And the intersection of what's on the right-hand side is x is less than or equal to negative 2, because if I'm looking at these two as sets, right, just follow the mouse arrow. I'm circling x is less than or equal to negative 2 and x is less than or equal to 3. Well, those represent two sets of numbers. Well, the only area that's common to both is anything that's less than or equal to negative 2, because that is true for both. For example, if I have the number, take an x value of 2. Well, an x value of 2 does fit the criteria of being less than or equal to 3, but it doesn't fit the criteria of being less than or equal to negative 2. And so I look at the common area because I'm trying to find the intersection. Now I have x is greater than or equal to 3 or x is less than or equal to negative 2. That's the union of those two sets. And I can draw the number line as follows. Okay, so I'm going to shade areas that interest me, and this is what it looks like. I've got negative infinity to negative 2 shaded with a bracket because the endpoint is included since it's less than or equal to. And I have 3 to positive infinity shaded with a bracket because 3 is included since it's greater than or equal to 3. Now you might be wondering, well, what are these gray lines doing here above the number line? For this particular example, they're not necessary, but in the next example you'll see how they're helpful. Just trying to get you warmed up a little bit. Okay, so the solution set is parentheses negative infinity, comma, negative 2, bracket, union, bracket 3, comma, positive infinity, parentheses. Alright, so this is a method that works great when you have a quadratic inequality and you only have two factors. Let's get on to an example that's a little more challenging. So this is a challenge problem. The way that I want you to do this is I'm going to give you the problem, and we're going to do two different checkpoints. The first that I'll have you do on your own is just setting up the problem and factoring it. But then I want you to resume at that point because I'm going to show you a new method to do these kind of inequalities that's going to be easier. Alright, this is the problem. Solve the inequality 2x cubed minus 3x squared minus 32x is greater than negative 48. Now, technically, this wouldn't even be a quadratic inequality. You could call it a cubic inequality, but the method of solving is really going to be similar. So the first thing I'd like you to try and do on your own is simply to rearrange terms and factor. And just a hint, you're going to need to group terms. We've done that a few times already. So that's the first challenge, is just pause the video, turn this into an inequality where 0 is on one side, and factor, and then resume when you have it factored or if you get stuck. Alright, going through the factoring, we bring the 48 to the other side because we want 0 on one side. Then we group terms. We take x squared out of the first two terms, so x squared times 2x minus 3. And we take a negative 16 out of the next two terms, and so we have negative 16 times 2x minus 3. Now it's clear from that step that the 2x minus 3 is just being distributed, so we can rewrite it this way. X squared minus 16 times 2x minus 3 is greater than 0. And noticing that x squared minus 16 is a difference of squares, we can expand that as well. We have x plus 4 times x minus 4 times 2x minus 3 is greater than 0. Alright, so that's the factoring. Now, before you go on, I want to teach you this new method, because notice that if you try to use the same method that we used in the last two screens, It's going to be tedious because you're going to have a lot of work. Okay, now let me explain that. We have three different factors here, and we want to get a positive number. Well, as you know, there are many ways to do that. You could have all three of these numbers be positive, x plus 4 positive, x minus 4 positive, and 2x minus 3 positive, and that'll give you a positive number. Or you could have any two of them being negative and the other positive. So the first negative and the second negative and the third positive, or the first negative and the next positive and the next negative, or the first positive and the next negative and the next negative. As you can see, that's a lot of things to test, and it's going to take you a long time. So here's an easier method when you have more than two factors. Okay, this is the method. You simply find the zeros, and from this factored form we can clearly see that the zeros are -4, 3/2, and 4. Plugging any one of those in for x will give you 0. Now those are the zeros, and the reason we find those is because now we can set up our number line, and we'll visually be able to find out what the solution set is. So we draw some vertical lines. This is where the vertical lines come in. What the vertical lines do is they divide the number line into intervals, and the vertical lines, as you can see, they go right through where the zeros are. Now that's because the zeros indicate where a function changes sign. Okay, now I'm going to give a graphical representation of that in just a bit, but here's the beauty of setting the number line, or dividing the number line up into intervals, is because then we can test representative values. For example, what if I put in the number 0, simple number 0. I put the number 0 in for x into this factored form. What would I get? Well, 0 plus 4 is 4. 0 minus 4 is -4. 4 times -4 is -16. And then I have 2 times 0 is 0, times -3, -16 times -3 is positive 48. Well, the beauty of this is that if anything in this region gives me a positive number, then every other thing in the region gives me a positive number. Okay, and the same is true in any other region. Let's say I plugged in the number 2. Well, 2 plus 4 is 6. 2 minus 4 is -2. And 6 times -2 is -12. And putting 2 in here, I have 2 times 2 is 4 minus 3. And that's just 1. -12 times 1 is -12. And therefore, everything in this region is going to be negative. So what I can do is I can write negatives or minus signs or plus signs above the number line to indicate what kind of region it is. Of course, when you're doing this on your own, you don't necessarily have to draw that many pluses and minuses. This is just for the sake of clarity. But what this does for you is when you test one number in a region and find out what its sign is, then you know the sign for every number in the region. Alright, and just to show you what this would look like on a graph, I'm going to show you now a different cubic function. This is a different cubic function, but it follows the same pattern as the graph of the cubic function that was given here. And this is just to give you a visual representation of why this is true on the number line. Notice that we have 3 zeros. I've got a 0 here, which looks like it's at about -1.3. I have a 0 here, which looks like it's about at 0.8 or so. And I have a 0 here, which looks like it's about 3.5. Okay, the actual numbers of these zeros don't matter. All that matters is qualitatively to see how this function behaves. Look, see, all of these function values here are negative, but then when it crosses the x-axis at the 0, well, we have a sign change. Now all the function values are positive, and that's true until I get to my next 0, where it crosses again, and then all the function values become negative again, and that's true until I get to my next 0, and then the sign changes and all my function values become positive. Alright, so that's just to show you why this works on the number line. If you find the sign of a function value for any x-coordinate in an interval, then you have found the sign for the function values of all the points in that interval. I can now fill in my solution set by shading the number line. Notice that the endpoints are parentheses this time, indicating that those endpoints are not included because the original sign was a greater than sign. It doesn't include 0. And so then I can write the solution set as parentheses -4 comma 3/2 parentheses union parentheses 4 comma positive infinity parentheses. And this is the solution set. Obviously, doing it this way is a lot easier than setting up all the different possibilities with disjunctions. One little word of warning before we conclude. Some inequalities have no solution, some have one solution, some have all real numbers as solution set. Now, that shouldn't come as a surprise to you because you've done inequalities before. But just be careful and proceed carefully as you're doing your steps, because if you end up with an answer that's no solution or only one solution or all real numbers, it doesn't necessarily mean that you're wrong. Classwork, page 204, numbers 11 to 25, odd. And we'll see you in class.